now from the carbonyl group, the aldehyde and ketones, to the carboxyl group, where there's a E group attached to carboxylic acids and derivatives. And we're going to start at the same place we started the aldehydes and ketones unit, with the review of the methods we already know for producing carboxylic acids. Probably the first thing that comes to mind when you think about synthesis of carboxylic acids is oxidation of primary alcohols. And we know that we can oxidize a primary alcohol by 1-butanol in this case, by treating it with potassium dichromate in aqueous acid solution. And because we're in aqueous acid, we get the over-oxidation product, butanoric acid. This was first introduced as a method that fails to produce an aldehyde, but if you're after the carboxylic acid in the first place, it works quite well. And you can also use the same conditions to oxidize aldehydes. Get the same product. In fact, the aldehyde is an intermediate on the way from the primary alcohol to the carboxylic acid, and the aldehyde is more easily oxidized than the alcohol. Which means that in practice it's impossible to stop at the aldehyde stage. And you probably remember that the mechanism proceeds through the hydrate. It's always formed in equilibrium with the aldehyde when you're in aqueous acid solution. And then by removing the elements of hydrogen, again, we oxidize that up to carboxylic acid. And this occurs through the intermediacy of chromate esters. Followed by an E2 elimination, where one of the hydrogens on the CH2 group is removed by water at base, break the bond between the oxygen and chromium and reduce the chromium 6, eventually to chromium 3. So we go through the chromate ester here, and then we form the chromate ester of the hydrate and do a second E2 elimination. So in the end, what we get is the carboxylic acid. Okay. So it's possible to use other oxidizing agents to oxidize aldehydes to carboxylic acids, and one that is used fairly frequently is nitric acid. reactants with H2O3. That's nitrogen in a +5 oxidation state, which is a relatively high positive oxidation state. And we know that good oxidizing agents include not only oxygen and halogens, but also metals like chromium in its high oxidation state, chromium-6 in this case, or manganese-7. But also nonmetals in a high oxidation state, like nitrogen in a +5 oxidation state, can readily be reduced. And we will get carboxylic acid out. And NO2 gas, where nitrogen is now in the +4 oxidation state. So we're doing a 1 electron reduction on the nitrogen. This is a 2 electron oxidation, so it actually requires 2 equivalents of nitric acid and generates 2 equivalents of NO2. And one could use the method of half reactions to balance that overall reaction if one wanted to. So oxidation of either primary alcohols or aldehydes will yield carboxylic acids. That is the first method, and probably the one that immediately came to mind. When we were talking about production of aldehydes and ketones, the second method that we talked about was oxidative cleavage of alkenes. And in fact, oxidative cleavage of alkenes can be used to produce carboxylic acids as well, by simply changing the second step to an oxidative workup instead of a mildly reductive workup. So, for example, cyclohexene will be oxidized first with ozone gas and dichloromethane, followed by hydrogen peroxide in aqueous solution to convert to adipic acid, or 1,6-hexane dioic acid, 6-carbon diacid carboxylic acid on each. And the intermediate is the ozonide, just as it would be for the production of the aldehyde, and then hydrogen peroxide will react the ozonide further to yield the carboxylic acid. So by merely changing the second step from mild reductive workup to oxidative workup, we can change the product from the aldehyde to the carboxylic acid. It's important to note that it must have a hydrogen on the double bond. If there were no hydrogen here, if this were a methyl group, for example, one would generate a ketone, not a carboxylic acid. So oxidative cleavage of alkenes is another useful way. And in the course of talking about the reactions of aldehydes, we talked about cyanohydrins. We talked about hydrolysis of nitriles. That's just a special case of hydrolysis of any carboxylic acid derivative. Perhaps the most common precursor to carboxylic acid is, in fact, other derivatives of carboxylic acids, like acid chlorides or anhydrides or esters. And this can happen either with reactive derivatives, like acid chlorides and anhydrides, in which case, in react spontaneously with water. Neutral nucleophile is good enough. So, for example, benzoyl chloride simply reacts with water to form benzoic acid. HCl. The mechanism for this is quite simple. Nucleophilic lone pair on the oxygen will attack the partially positive carbonyl group, pushing the pair of electrons out onto the oxygen. That's reversible. And then the lone pair, one of the lone pairs on the oxygen, becomes a reforming carbon oxygen bond and kicking out chloride, which is an excellent neutral. We then just a proton transfer away from generating our benzoic acid. And since we're in aqueous solution and HCl is completely dissociated, we don't really have HCl, we really have the hydronium ion and chloride ion. So it's a three-step mechanism. Nucleophilic attack, followed by loss of equilibrium group, followed by a proton transfer. And this is quite a general mechanism. This is the standard mechanism for nucleophilic acyl substitution. When the substitution reaction is happening at a carbon-oxygen bond, the nucleophile is not leaving out directly. Instead, it donates into an anti-bonding pi orbital, breaks the pi orbital, and in the second step, the group leaves. So, nucleophilic attack, loss of leaving group, and then since the nucleophile is neutral in this case, in order to get a neutral product, we need a proton transfer. There's often a proton transfer in base-catalyzed reaction with acid derivatives as well. Anhydrides react by an identical mechanism. And you, in fact, did a reaction of a phenol with an anhydride in the first semester general chemistry class to synthesize aspirin or acetyl salicylic acid. Generating as the other product acetic acid. So this is acetic anhydride. The mechanism is also a nucleophilic acyl substitution. The nucleophilic lone pair of phenol attacks carbon to carbon. So again, step one is nucleophilic attack. And the anhydride is a good enough nucleophile. Sorry, phenol is a good enough nucleophile and the anhydride is a good enough electrophile to interact directly the nucleophile doesn't require a negatively charged nucleophile. We have a tetrabutyl intermediate. General feature of the nucleophilic acyl substitution. Notice we also have tetrabutyl intermediate here. In case of the acid chloride, the lone pair on the negatively charged oxygen now comes in and kicks out the acetate ion as the leaving group. And in these cases where the leaving group is very good, that loss of the leaving group is unlikely to reverse. We now have a protonated ester. Acetic acid can now take that proton off to generate aspirin. So in this case, the product is an ester. But if the nucleophile, instead of being the phenol in this case, had been water, we could have done an identical reaction generating similar intermediate, also the leaving group. Transfer either of these two protons. To, in this case, generate two molecules of acetic acid. And that's, in fact, how you used up the excess acetic anhydride in your aspirin synthesis. After the aspirin synthesis was complete, you simply heated it until the oily acetic anhydride that was kind of floating on top disappeared, proving that it had been converted to acetic acid. And then you cooled it down to crystallize out the aspirin. So you'll notice that the hydrolysis of carboxylic acid derivatives is a way to make carboxylic acids, but reaction of those reactive carboxylic acid derivatives, like the acid chloride and the anhydride, is also an entry point to other acid derivatives, such as, in this case, the ester functional. So we'll see that nucleophilic acyl substitution mechanism repeatedly throughout chapters 19 and 20 as a way of converting one carboxylic acid derivative into another. So when you have the anhydride and the acid chloride, the reactive carboxylic acid derivative, the nucleophile is simply neutral water. Esters and amides, however, and nitriles are stable to water, but can be hydrolyzed in the presence of hydroxide ion. fact, they can be hydrolyzed with strong aqueous acid or strong aqueous base. We saw already, for example, the hydrolysis of a nitrile in concentrated aqueous acid, or catalytic concentrated aqueous acid, so water, and perhaps some 12 molar HCl. And that mechanism is presented when we were going through chapter 17, talking about cyanohydrates. It's also possible to hydrolyze a nitrile in the presence of base. We'll see in a minute. And it's possible to take an ester in this case, methylpropanoate, and treat it with aqueous ammonium ion, aqueous acid, and generate propanoic acid and ethanol. This mechanism is a little bit more complex than the simple nucleophilic acyl substitution mechanism that we saw in the reaction of acid chlorides and anhydrides. This mechanism, which is in equilibrium, is actually 6 steps, and it is the reverse of ester synthesis by the Fischer esterification. So the mechanism will be to start by protonating carboxylic acid oxygen. And if you're in doubt as to which oxygen you should protonate, keep in mind the great rule of organic chemistry that says to understand the reactivity, take a look at the minor resonance contributor. In this case, the minor resonance contributor has that single bond to oxygen with a negative charge on it. So this oxygen has a significant partial negative charge on it. This oxygen does not. You'll see that the intermediate, that one here being proton transfer, the intermediate now will be resonance stabilized, whereas protonation on this oxygen would not be able to resonance stabilize the intermediate. This carbon now is subject to attack by a nucleophile. And where water was not a good enough nucleophile to react spontaneously with the ester carbonyl, now that it's positively charged, it is a good enough nucleophile to react. So step 2 is a nucleophilic attack. And we'll see that this mechanism is similar to some other mechanisms we've seen in the past, where it goes in sets of 3, where there's a protonation followed by something else, followed by a deprotonation. In this case, step 2 is a nucleophilic attack. Steps 3 and 4 will be proton transfers. Step 5 will be the loss of the leaving group. And then step 6 will be another proton transfer. We have a tetrahedral intermediate. And after step 3, that will be a neutral tetrahedral intermediate, where we're taking a proton off. and converting the carbon that used to be the carbonyl carbon into a temporary intermediate with two OH groups and an O, in this case, an OET group, an OR. The goal of steps 3 and step 4 are to get the proton from this oxygen onto this oxygen so that ethanol can leave as a leaving group. So our next step is another proton transfer. In this case, a protonation rather than a deprotonation. And now ethanol can leave, and we can even push it with one of the lone pairs from the other two oxygens. Go to step 5, the loss of the leaving group. And ethanol we're just one step away from our final product now. And if the concentration of water is kept fairly high, so the concentration of ethanol is low, our final proton transfer step we'll use water as the base to generate the neutral propanoic acid and regenerate the hydronium ion that we used in step 1. So the catalyst is regenerated. Working with dilute sulfuric acid or dilute HCl, 3 to 6 molar. Ensures that the equilibrium lies towards the carboxylic acid and the alcohol by Lechappe's principle, keeping high concentration of water and a low concentration of alcohol to push that equilibrium towards the right. To do the Fischer esterification, the forward version of this reaction, we would simply use a small amount of catalytic acid and ethanol as our solvent, and in the presence of a large excess of alcohol, we would push the equilibrium towards the acid. So this mechanism is important. We will definitely be called upon to reproduce this mechanism in either one direction or the other at some point. 4 proton transfers, a protonation followed by nucleophilic attack, followed by a deprotonation to generate a neutral temporary intermediate, and then another protonation followed by loss of the leaving group, followed by a final deprotonation to generate the product. And that reaction can go in either direction depending on the concentration of water versus the concentration of alcohol. It's also possible to hydrolyze a nitrile or an amide in aqueous acid. By a mechanism that's quite similar, but where the leaving group will be a neutral amide rather than a neutral alcohol. In fact, after the first step, the protonation of the carbonyl oxygen of the amide, you'll recognize that the intermediate is identical to the intermediate that you've already seen in the hydrolysis with the nitrile. And you should remember from last semester that in aqueous phase, we can convert an ester to a carboxylic acid. acid salt. And the alcohol. This reaction is referred to as saponification. As we see so frequently, when we're doing a reaction in base, it's fewer steps than when we're doing a reaction in acid. In fact, in base with a negatively charged nucleophile, the hydrolysis of an ester to yield a carboxylic acid is the identical three-step nucleophilic acyl substitution mechanism that we saw in the reaction of the reactive acid derivatives. Step one is the nucleophilic attack. This is the equilibrium. Step two is the loss of the lead group. It's a very unfavorable lead group. Alkoxide ions are strong bases, and so they don't really want to leave. The equilibrium is driven forward by an irreversible proton transfer in step 3, where we have an acidic carboxylic acid proton with a pKa around 15 being removed by a fairly basic alkoxide ion. Technically, this is an equilibrium, but we can calculate the equilibrium constant knowing the pKa of the acid and of the conjugate acid. And since the pKa of an alcohol hydrogen is about 15, and the pKa of carboxylic acid is about 5, the equilibrium constant here approximately 1 times 10 to the 10th. The carboxylic acid is 10 orders of magnitude more acidic than the alcohol. The alcohol is a much weaker acid, so that equilibrium lies pretty much all the way to the right. So 3 steps: nucleophilic attack, loss of the leaving group, proton transfer at the end. The difference being that now the product is the carboxylic salt, because we started with a negative charge instead of a positive charge. This same mechanism can be used to hydrolyze an amide. The leaving group would simply be an amide ion, which is an even worse leaving group. But again, it can be convinced to leave if you promise it a proton. Alkoxide doesn't want to leave. Alkoxide said, I'm a oxide, I'm a really strong base, I'm going nowhere. And the molecule says, yeah, but if you leave, you can have this proton in the next step and become alcohol. And it really likes that, so it takes the market. So hydrolysis of the less reactive acid derivatives, the ester, the amide, the nitrile, is a good route to carboxylate salts, which can be protonated to yield carboxylic acids with a negatively charged nucleophile. The fifth way, which is commonly used for aromatic, is to react alkyl magnesium bromides with carbon dioxide. And it's commonly introduced as carbon dioxide solid or dry ice. So, for example, if you had bromobenzene, you could add magnesium in the presence of ether to generate phenylmagnesium bromide. Phenol magnesium bromide is in fact the Grignard reagent that we made in the first lab of the semester. This can be reacted with ketones or with aldehydes to generate tertiary or secondary alcohols, respectively. But if it's reacted with CO2, the negatively charged carbon can simply do a nucleophilic acyl addition reaction. To add the phenyl group and the magnesium bromide across the carbon oxygen bond, aqueous acid in step 2 will then protonate one nucleophilic attack, a 2 proton transfer, to generate the carboxylic acid. And if it were HCl, for example, often about 1 molar, the chloride is the counter ion, spectator ion in this process. So it's a very simple mechanism. This is just an insertion of magnesium to convert the aryl bromide to the Grignard reagent, and then we have a nucleophilic attack, followed by a proton transfer. We've effectively added the elements of benzene across the carbon oxygen double bond. The nucleophile being the phenyl group, the electrophile being the aqueous acid. The method is limited, obviously, because this is a strongly basic reagent. You can't have a carboxylic acid or a alcohol anywhere in the molecule, or you can get protonation. And since you know that organometallic reagents react with the carbonyl group of aldehyde and ketones, you can't have an aldehyde or a ketone elsewhere in the molecule. And I think that is, there's one more reaction I do want to talk about for synthesis of carboxylic acids. And that's a special case of the reaction just presented. Is the reaction of phenols and CO2. The reaction of a phenol with potassium carbonate, CO2 solid, and water is referred to as the Colby reaction, and you'll find this hiding in chapter 22. Because of the greater acidity of this hydrogen, pK of around 10, we can use a pretty weak base, in this case potassium carbonate, to remove it, to generate an oxide ion. And that actually can switch those ions. So the other resonance structure. So carbonate ion is a strong enough base to take that proton off. Generating the bicarbonate ion as a byproduct. And this you'll recognize as an enolate ion. We've got an O- on a double bond. It has a resonance structure puts the negative charge on the carbon ortho to the phenol. This is now a good enough negative charge to react this carbon with carbon dioxide. Bicarbonate ion is certainly a good enough base, or enough acid rather, to propagate this carboxylic acid. Regenerate the carbonate ion. And you'll recognize that this is now the keto form. And all that we would need to do to regenerate the aromatic ring is a keto-enol polymerism, where protonating the oxygen and deprotonating that carbon turn the double bond ring, regenerate the phenol, and make salicylic acid. So the Colby reaction is an effective method under much milder conditions, using only potassium carbonate as the base, to react a phenol with carbon dioxide to generate a 2-hydroxy carboxylic acid, salicylic acid, also known as 2-hydroxy benzoic acid. So what we'll do in the next video is talk about the various factors that affect the reactivity of the carboxylic acid derivatives. What is it that makes the acid chloride and the anhydride good enough electrophiles to react with neutral nucleophiles like water, whereas the esters and amides only react with negatively charged nucleophiles.